Good morning, everybody. Hope you can see can see the screen and the presentation. Who is attending remotely can see also the presentation. This is Pietro from Nextworks. Today's presentation is about the usage of TeraFlowSDN as a control plane for the next generation central office. And in the slide, we will explain what it is, this NGCO in a hybrid TSN and optical environment. This is basically the outline of the presentation. Before going directly and straight to the usage of TeraFlow in this project, this is just a brief overview. There will be a brief overview of the project itself, stating the motivation, the main objectives, and what are the scenarios where TeraFlow will be used. Then, of course, we will move to the more software part, explaining how TeraFlow will be used and potential extent to support this control plane of TSN and optical network. So let's go step by step. So what is OCTAPUS? OCTAPUS is an European funded project, which duration is about 3.5 years. Was started last year, September 2022. And briefly, the motivation about the project is that the skyrocketing demanding of bandwidth, but also requirements in terms of latency are becoming more and more challenging. So this basically led for a call for a new architectural changes into the network at the key aggregation point called the central office. So in a very few words and roughly speaking, these central offices needs to be upgraded. And that's the reason of the next generation central offices. As you will see in the next slides, these next generation central offices is an ecosystem where different TSN and not TSN devices are interconnected to each other in order to satisfy the the requirements into the motivation. Of course, you can find more and more information to the related website, and if you, are interested in. So what is next generation central offices? Is, as I said, an ecosystem composed by different components, TSN and not TSN component. For who is not familiar with the TSN, TSN stands for time-sensitive network, is basically a way to have some very strict latency requirements in terms also of under the milliseconds. Of course, there are plenty of standards about the time-sensitive network for the clock synchronization, for the requirements, for the TSN flows management, so on. This is, of course, out of the scope of the presentation, but just provides, a very rough idea what TSN is. But coming back to the NGC architecture, basically there are these three main components. So the uplink switches, the OCS, and the interface cards that are part of the ecosystem, of the NGC ecosystem. As you can see, there are two uplink switches, which, from a theoretical perspective, the maximum capacity is around 25 terabits per second. And that are connected to the OCS, which are optical devices that are not TSN enabled. And on the other side, there are the interface cards, which are TSN enabled too. Here, where the control planes comes into play, because basically this device has to be controlled in order to satisfy the high-level requirements. So in one side, we have the TSN domain, where the uplink switches and the interface cards talks the, let's say, TSN language. In particular, there is a specific, there is a specification of IEEE that they will use for the TSN flows management, but other specifications that are used for other purposes. And on the other side, we have, let's say, the optical world made by these OCS, which are basically the optical circuit switching that are able to switch on a straight line, either on a straight line, on on a cross configuration in order to serve one of the interface cards on the on the right side. And to do so, to implement these flows, the TSN flows, two actors are needed for the at least for the TSN part, the CUC and the CNC. The CNC is basically TSN SDN controller, while the CUC is the entry point of the TSN flow requesters. So we have basically TSN flows management in a hybrid network, and this is one of the challenge of the project. This is where the SDN coordinator comes into play. This is one of the target scenarios. So we basically have zoomed out the control plane to see where it's placed in an end-to-end network. We have on a Paris neighborhood. I don't know the correct French pronunciation, is arrondissement, something like that. Sorry for that. Where there are a dense area use case. And there are different G0B connected through a passive optical network to this NGTO, in particular to the interface card. Of course, a lot of user equipment would require some traffic requirements, sorry, up to the 5G core network. And the NGTO in this end-to-end network sits more or less, in the middle. And different types of traffic needs to be managed. So we have the best effort standard Ethernet traffic. We have the TSN flows, which are more restricted in terms of requirements. And we have the express traffic, which somehow bypass the whole NGTO in case the requirements are, from health scenario or something like that. Here again, the SDN coordinator comes into place to manage the flows within the NGTO. So managing all the, not only the configuration, but also the balancing between the two uplink switches that in some cases could result in an unbalancing. And last but not least, we have within the project to make some experimental validation, not only in the lab trial, interacting the different single components, but also with the final in the final demo of the network operator premises. So this more or less summarizes the scope of the project, the NGTO, and what are the role of the control plane, in particular the SDN coordinator. So doing this, we envisioned this is the functional architecture of the SDN coordinator. This is a very high level because you can see here the TSN domain and the optical domain. And the SDN coordinator basically sits above of these two domains. So on one side would talk the TSN language, in particular the IEEE 802.QDJ specification for the TSN flows management. On the other side would let's say talk the let's say optical domain language. So here the challenge for the SDN coordinator is to have end-to-end and global view about this hybrid network, and to satisfy the requirements, TSN requirements and non-TSN requirements coming from the listener talkers, which are basically the two entities that would ask for the TSN flows provisioning, and the network operator that usually makes some configuration, visualization, and operation that for the management of this end-to-end network. So if there are questions, please interrupt me. I can explain you any other points if needed. By this, we've identified some internal building blocks within the SDN coordinator. So the topology for collecting all the information related to the devices, or components within the end-to-end network, but also the resources. Provisioning for managing different TSN and not TSN flows within this end-to-end network. the PC for the path computation, because at the end, having this complex internal end-to-end network, we have to find the best way, given some also some constraints, to compute the path. And then we have the monitoring and routing, because as I was saying, some internal load balancing will be needed. So we need first to check the status of the network, the different flows, and where these are located. And then if an unbalancing is identified, then we have to move some flows to one uplink to another. And last but not least, we have also the southbound interface to talk with both domains. So having identified these internal building blocks, we've exploited TeraFlow to map these internal building blocks to existing TeraFlow's component. So most of them can be mapped one-to-one with TeraFlow. For instance, we can map the topology with the context, because at the end is some sort of inventory where all the information about devices, resources are stored. For what concerns the provisioning internal building block, we identify the slice TeraFlow components, because TeraFlow slice component, because basically some constraints within the TSN flows can be mapped within the slice. So for instance, the delay, the jitter, whatever is concerns the time domain. Path computation, for obvious reason, could be mapped to the path comp of TeraFlow one-to-one, as well as the monitoring. For what concerns the rerouting, the policy and automation would help us to identify, add some rules and perform some actions based on some condition on the end-to-end network. Also, the southbound and device component can be mapped one-to-one, because at the end, these plugins can be exploited and used. What will be new in TeraFlow, at least within the OCTAPUS project, is the CUC, which is basically the entry point for the TSN requests. Currently, at least in the version 2, in the release 2 we are using, is not available this component. So this could be, at least within the project, an extension to support the TSN flows requests. And then last but not least, we have the management system, which is basically the web graphical user interface. Currently, there is no support for the management of the TSN flows, so could be extended, adding some options or minor features to, at least within the OCTAPUS project, in order to have this kind of support. So this is the architecture of TeraFlow. I just realized that is not the most updated version, because some naming is different, like device with southbound interface, the compute with the NBI. But the extensions here mentioned in this bullet point list are still valid. Basically, here there is the possible and potential usage and extension of the different TeraFlow software component mentioned in the previous slides. This is just a little bit of detail, saying that, for instance, some data models in the TSN domain and the optical domain can be supported, can be a software extension within the context component, as well as the device, because there is no support for interacting with the TSN domain. And of course, the other possible extension you can see here in this bullet point list that are possible in the release 2 we are currently using. So from a project perspective, we are in the we are completed the design phase. We are starting to deal with the development phase. We start to make some minor extensions to TeraFlow in order to support what is needed for the project. And some of the components, as you can see here, are out of the scope because the distributor, but also centralized attack detector is not the part of the scope of the project. What we could be interesting in is the forecast component that would make more, smart the balancing of the TSN flows within the end-to-end network. But of course, this will be more seriously taken in consideration in the future releases of the development. So these just are some initial tests with the TeraFlows and a NextGen agent, which is based on the netconf protocol. For whoever that doesn't know, this NextGen is just an open source SDN agent based on, that uses the netconf protocol, implementing the basic RPC like getconfig, and so on. And it supports the extension, giving the young model of a specific device, the generation of some models that need to be extended from a software perspective in order to support the logic. We've used just to make some initial development and tests. As you can see here on the bottom part, we just extended the device enumeration for supporting the OCS device, which is optical circuit switch device, and include also some initial edit config and get config for reusing some available code in order to make some initial requests. But as I said, this is just an initial test to play with the TeraFlow. I think that's all. So this is just a sum up of the presentation. So saying that what is OCTAPUS, what is the NGCO, why we have chosen TeraFlow, and how the internal the mapping between the internal components of the SDN coordinator and the TeraFlow components is made. Some very initial developments, extensions, and tests to support these optical circuit switching device operations. And of course, the work to be done is in the next steps. So we have to, of course, extend the data model based on the IEEE QDJ specification, which is basically in charge of managing the TSN flows that currently, at least in the release 2 we are working in, is not available. And of course, we have to extend the plugins and add this new component, which is specific to this purpose in the TSN domain. And last but not least, we have to make some integrations with the optical and the TSN network in order to progress with the not only with the development but also with the integration. And eventually, everything should be validated with the not only with the real network but also with the end-to-end network into the final team. I think that's all. I don't know if you have any questions.
For this extension that you were mentioning, you are really well. I understood it's still under design and you are devising how to address all and align everything. Whenever you have then more or less clear view, feel free to create the issues in the tracker, and for sure we can try to allocate the slots in the tech calls to properly discuss how to align all the different enhancements and new features, and especially this CUC new component that you were mentioning.
That one here,
exactly.
Yes, because I mean, one thing that maybe I didn't explain too much is that, I mean, if we are considered TSN flows only, so only the TSN domains, there will be document listeners, UC, and the TSN words. But here, basically, we have also the hybrid. So, I mean, we have this kind of situation where we need the CUC, we strictly need the CUC to follow the specification. Yeah, it is application specific. I mean, the initial idea is to have like a separate component because unfortunately we didn't see any other component that is application specific and specific to satisfy this kind of requirements. So there is to have a new component beyond beyond the still available. But yeah, I think we should discuss the design choice first to see if this could fit within either an already existing component or should be, a brand new component.
It's important. The presentation is great. I think it's important that we analyze if we can break the CUC into some part in service component and some part in the device component. Because device is like the software interface. So I guess that you will be talking to the TSN API using the RESTConf live.
Okay.
Or I don't know if it will be RESTConf or NetConf. We'll be talking like
okay.
API model.
Currently, I mean, this CNC component is developed by another partner in the consortium. We are discussing either NetConf or RESTConf interface through this northbound interface. Currently, the choice will be NetConf, even if honestly I don't like too much because it's a application level, but is their component. But in any case, RESTConf is just a REST version of NetConf. So I mean, moving from NetConf to RESTConf should not be a big deal, but yes, that could be. On the table is a point on the table. And for your first point, I mean, since there is no, I mean, one idea could be that, for instance, just maybe I'm thinking aloud, when you ask to create a service, okay, if, for instance, I'm thinking like how the code is structured, if it's a TSN service, then this request maybe could be, forwarded or sent to the CUC that will manage this kind of service. But, it's just a first thought and needs to be discussed more in depth.
Yeah, but there is no difference into having a CUC driver inside service. So then you have all the workflow, following the workflow, the standard workflow.
Okay.
Okay. So it's like we have the concept of driver for plugins, let's say, for the service to provide also this kind of behavior. And that you don't need to worry about the rest of the workflows in TeraFlowSDN. This could be also a solution.
So, for instance, I'm thinking into the code perspective will be some sort of service handler specific for the CUC, for instance, that will manage. Yeah, could be a solution. Yeah.
But it's very much very interesting, and it's a very new usage of the TeraFlowSDN. So, thanks for presenting it.
Thank you.
Any other questions on the room or on the chat, or on just turn on your mic?